In this video, we're going to look at the potential energy due to a spring. In a previous video, we looked at the work done by a spring as we compress it or stretch it from some initial position to some final position. The position of the spring is defined as the distance it's been compressed or stretched away from equilibrium, where stretching is positive x and stretching is positive x, compressing is negative x. Okay. So we learned how to calculate the work done by the spring. We did this using an integral. And it turns out that the spring force, this Hooke's law force that describes the force exerted by a spring, is in fact a conservative force, which means we can write down a potential energy associated with the spring. That potential energy turns out to just be 1/2 kx squared. So I'm going to show you how that works real quick, and then we'll go through and solve a few problems involving spring potential energy. So in a previous video, we calculated that the work done by a spring equals 1/2 k times x initial squared minus x final squared. X initial is the initial position of the spring. X final is the final position of the spring. Well, for any conservative force, the change in potential energy due to that conservative force equals minus the work done by this conservative force. In this case, the conservative force is the spring force, so we're calculating delta U spring. This equals minus W spring, minus the work done by the spring. So this just equals 1/2 k x final squared minus x initial squared. The minus sign just switches the order of the subtraction here. Let's do two things. Let's define our 0 point of potential energy to be x equals 0. So we'll say at x equals 0, u equals 0. And now let's say delta u s, well, it equals u final minus u initial. And this equals 1/2 k x final squared minus x initial squared. Let's say x initial equals 0, which means that u initial equals 0. So we get 0, and here that goes to 0. So we just get u final equals 1/2 k x final squared. This is true for any x final, so this shows that u, the potential energy of the spring, just equals 1/2 k x squared. This is the formula we're going to use the potential energy for the potential energy of a spring. But remember, this only works if we define the potential energy to be 0 at x equals 0. Remember, for the gravitational potential energy, we said you can make the 0 point of gravitational potential energy whatever you want. You can make it the surface of the table, you can make it the floor, you can define that to be wherever you want it to be. Well, for a spring, if we're going to use this formula, we have to say then that the potential energy equals 0 at x equals 0. Otherwise, this formula doesn't work. If I make a graph of the potential energy u as a function of x, it looks like a parabola. It's proportional to x squared. So at u equals 0, that just means my spring is relaxed. It's neither stretched nor compressed away from equilibrium, such that it's relaxed length. And this is x equals 0, so that gives me 0 potential energy. Positive x means I'm stretching the spring away from equilibrium. That is, I'm pulling on the spring, stretching it out, and increasing its potential energy. So stretching the spring increases its potential energy. For x less than 0, well, that means I'm compressing the spring, I'm squeezing it together like that. X is negative, but I still get positive potential energy. This spring potential energy is always greater than 0. It increases if I compress the spring, it increases if I stretch the spring. So no matter what I do to a spring, it will store positive potential energy and be ready to give that potential energy back in the form of kinetic energy. That is, it's always ready to spring back to its relaxed length. Let's look at a conceptual question. A spring is initially compressed 10 centimeters from its equilibrium position. It uncompresses, launching a block across a surface at 2 meters per second. What will the velocity of the block be if the spring is initially compressed by 5 centimeters instead of 10 centimeters? Will it be 0.5 meters per second, 1 meter per second, 2 meters per second, or 4 meters per second? So take a minute, pause the video, think about your answer, and come back when you think you have one. Well, right away looking at this, if I compress the spring 10 centimeters, well, that gives me potential energy. That stores potential energy in the spring. So when it uncompresses, that potential energy gets converted into kinetic energy. That gives the block some speed, because kinetic energy is 1/2 mv squared. So if I compress the spring by a smaller amount, only 5 centimeters instead of 10 centimeters, well, then I should have less potential energy. The more the compression, the greater the potential energy. So I have less potential energy, therefore I should have a lower speed when the block launches. So right away I can eliminate C and D. It can't be C or D, it has to be A or B. The block should come off slower if I compress the spring by less. So once again, pause the video, take a minute, and come back when you have an answer. So to answer this question, let's think about conservation of energy. Initially, we have some energy, E initial. This has to equal our final energy, E final. Well, E initial, when we compress the spring, what we have is spring potential energy. After the spring uncompresses, well, the spring loses its potential energy and turns that into kinetic energy. K final. So we can say 1/2 K x initial squared equals 1/2 m v final squared. So what this shows is that the final velocity squared is proportional to the initial compression of the spring squared. V final squared is proportional to x initial squared, which means that V final is proportional to x initial. I can take the square root of both sides. So if I compress the spring by half as much, the block should launch with half the velocity. So if I compress the spring by 5 centimeters instead of 10 centimeters, it should come off at 1 meter per second instead of 2 meters per second. Having the compression of the spring should have the final velocity of the block. So the right answer is B, 1 meter per second. So the spring potential energy, unlike gravitational potential energy, which is linear in displacement, it's just proportional to how far I lift something, the spring potential energy is proportional to the square of how much I compress the spring. But that means that if I double the compression of the spring and then release the block, I just double the velocity, since the kinetic energy is also proportional to velocity squared. Okay, let's do an example. You drop a block with a mass m equals 2 kilograms from a height h equals 40 centimeters above the top of a spring with a spring constant k equals 400 newtons per meter. We want to find the speed of the block when it hits the spring, the maximum compression of the spring, and then we want to find what the compression of the spring is when the block comes to equilibrium. Okay, so let's kind of start by drawing a little diagram of what's going on here. We've got our block up here, mass m, and here's our spring, boop, 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 like this. We'll put a little platform that the block can land on. And this block starts out a height h above the top of the spring. So I'm going to call this position 1. Then the block falls and hits the top of the spring. So we've got our spring here, like this, but the spring is uncompressed. I'm going to call this position 2. Then the block compresses the spring down to some final compression below its starting point. Let's call this compression here x final. This will be position 3. And then eventually the block comes to equilibrium. It's going to bounce up and down around that position for a while until it comes to some equilibrium position here, where the spring is compressed by some equilibrium amount. Position 4. We'll call this X equilibrium. Okay. So, part A, we want to find the speed of the block when it hits the spring. Well, let's do this using energy. So we're going to start out with the work energy theorem. The work done by external forces equals delta K plus delta U plus delta E thermal, and we won't worry about E internal. All right, so what are the forces acting on the system? Well, there's the gravitational force on the block, and there's the spring force that acts on the block when the block hits the spring. If we consider our system to be the block and the spring, and then Earth down here, which is exerting a gravitational force on the block, down here we have Earth. If we consider this to be our whole system here, then all of these forces are internal forces. They are all conservative forces, so we can treat all of these forces, spring force and gravitational force, as sources of potential energy. Therefore, the work done by external forces is 0. There are no external forces. This is an isolated system, so that's just 0. And there are also no dissipative forces here. There's no friction or drag or anything like that. So delta E thermal just equals 0. So we can say that 0 equals delta K plus delta U. And we can write this instead as K final plus U final equals K initial plus U initial. All right. So this is going to be this form of conservation of mechanical energy, where energy is just transformed from kinetic to potential energy, is what we're going to use to solve this problem. And for any conservation of energy problem like this, we need to have an initial position and a final position of the system. For this, we're going to call this our initial position, position 1, and position 2 will be our final position. Okay, so let's write it this way. K2 plus U2 equals K1 plus U1. All right. Now, what we can say is that let's go ahead and call this uncompressed position of the spring, let's also call it the 0 point of gravitational potential energy. Remember, we can say the gravitational potential energy is 0 wherever we want. Here we're going to call that the same as the 0 point of spring potential energy. So that means that position 2, when the block hits the spring, the final potential energy here is just 0. There's no gravitational and no spring potential energy. So we just have 1/2 m v2 squared, that's the kinetic energy at point 2, equals, well, V initial, we're just going to drop this block from rest, so K1 equals 0. There's no kinetic energy when we start. And the potential energy, well, this would be the gravitational potential energy plus the spring potential energy. Here we're dealing with 2 types of potential energy. Gravitational potential energy is mgh. That's the potential energy the block starts with. And the spring potential energy is just 0 when we start because it's uncompressed. Okay, so we just get 1/2 mv2 squared equals mgh. So this gives us v2 squared equals 2gh. So v2 equals the square root of 2gh. If we plug in our numbers, this gives us v2 equals 2.8 meters per second. So when the block hits the spring, It has a speed of 2.8 meters per second. Okay, part A is pretty easy. The spring doesn't even matter here. We're just transforming gravitational potential energy into spring potential energy. Now, part B, what is the maximum compression of the spring? Well, to find the maximum compression of the spring, we're going to still need to use conservation of energy, but now we're going to think about what happens when the block reaches this position 3 here, and the spring is compressed by the greatest possible amount. All right, I move things around a little bit to clear up some space. So for part B, well, what we're going to do is use this position 1 as our initial position, and we'll use position 3 as our final position. We want to conserve energy between this point where the block is up here and this point down here where the spring reaches its maximum compression. So we'll have K3 plus U3 equals K1 plus U1. Okay. So first of all, when the block starts, we release it from rest. So that means K1 is still 0. When the spring reaches its maximum compression, well, the block is going to push the spring down, and then it's going to stop, and then it's going to start to go up again. When it stops here at the bottom, the velocity of the block is 0. So that means that K3 also equals 0. So when the spring reaches its maximum compression, we have 1/2 K, actually let's just write this out first. We have U spring at position 3 plus U gravitational at position 3 equals U gravitational at position 1. So this is our conservation of energy formula. It's just potential energy being transformed from one type of potential energy, gravitational potential energy, into another type, spring potential energy. Okay. So now let's plug in the formulas for what these are. Our spring potential energy at the end, well, we called this distance here x final. So this is going to be 1/2 K, and since it's being compressed, this is a negative distance, so it's negative x final, but then that whole thing is squared. Our gravitational potential energy, well, it's below the 0 point of gravitational potential energy. So this is going to be plus mg. The final height is minus x final. That is, it is a distance x final, the same distance the spring is compressed. The block is that distance below its 0 point of gravitational potential energy. So we have to include that gravitational potential energy there. And then this equals mgh. That's our initial gravitational potential energy. Okay, so now what I have here is actually a quadratic formula in terms of x final. I have an x final squared here, an x final to the first power, and x final to the 0. So let's write it like a quadratic equation. I have 1/2 K x final squared. The negative sign squares out. Minus mg x final minus mgh equals 0. So this here is my A. This here is my B. And this whole thing is C. A is 1/2 K. K is 400 newtons per meter, so A equals 200 newtons per meter. B is minus mg, so this is minus 2 kilograms times 9.8 meters per second squared, which is minus 19.6 newtons. And C is minus mgh. H is 40 centimeters or 0.4 meters, so this equals minus 7.84 joules. Okay, so now I'm going to plug all these into the quadratic formula, which says that x final equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So if I plug this into my calculator, I get this equals 0.253 meters, or negative 0.155 meters. We're going to throw away this negative solution. This is our correct solution here, 0.253 meters. That's how much the spring is compressed, about 25 centimeters before the block stops, turns around, and starts to go back up. Okay, so we used conservation of energy to solve this problem. And in this case, rather than energy just being transformed from potential to kinetic energy, it was transformed from one type of potential energy, gravitational potential energy when it's up here in the air, to a different type of potential energy, spring potential energy, plus a little bit of gravitational when the spring is compressed. Okay, for part C, what is the compression of the spring when the block comes to equilibrium? Well, this block is going to bounce up and down on the spring for a while until it kind of comes to rest at some equilibrium position. And this means that the net force acting on this block equals 0 when it reaches equilibrium. So part C actually isn't an energy problem, it's a force problem. And the exact details of how this block bounces up and down and comes to rest we'll learn about later when we study harmonic motion and oscillations in the last couple weeks of the course. But for now, all we have to do is, well, we have to draw a free body diagram for the block. So here is our block here. There are two forces acting on the block when it's in contact with the spring. There is a spring force, which is going to push up on the block, like that. And there is a gravitational force, which is going to pull down on the block, like that. And we can just write out Newton's second law in the y direction. F net y equals may. Well, the acceleration is going to be 0 when the block comes to rest and it reaches equilibrium. So we just have the spring force pushing up in the y direction minus the gravitational force pulling down. This equals 0. This spring force, well, the formula for the spring force is minus kx, but the minus sign is just telling us the spring force points opposite the direction of the compression of the spring. So if the spring is compressed down, spring force pushes up. So the magnitude of the spring force is just k times x minus mg equals 0. And if we solve this equation for x, we get that x equals mg over k, which is, well, mg is 19.6 newtons, k is 200 newtons, sorry, wrong, k is 400 newtons per meter. So we put this into my calculator, and I get 0.49 meters, which, actually, sorry, it's 0.049 meters, which I can write as 4.9 centimeters. So this is my equilibrium compression of the spring, XEQ, equals 0. Let's write it as 4.9 centimeters. Okay. So just to be clear, what's the difference between this X equilibrium here and this X final from part B? Well, X final is the maximum compression of the spring. As this block bounces up and down on the spring, this is as much as the spring is ever compressed. This is max compression. This is our equilibrium compression. This is our compression when the block eventually comes to rest. So we'll say compression at equilibrium, when the block stops bouncing up and down and comes to rest. So to find this maximum compression, we have to use conservation of energy. To find this equilibrium compression, we use Newton's second law. Okay, so that's a nice spring problem. It involves using Hooke's law to find the force. It involves using our potential energy formula to find the potential energy of the spring, and using conservation of energy to see how gravitational potential energy is converted into spring potential energy. Okay, that's pretty much all I want to say about springs. In the next video, we will look at potential energy graphs.